Well, thank you so much, Erwin and Igor, for organizing this wonderful meeting and inviting me to be a part of it. So I am a biophysicist, and my general interest in active matter is trying to understand principles of life and emergence of collective behavior in these systems that are inherently far from equilibrium. I don't see the need to define active matter because I work with living systems, though I would say that I thoroughly enjoyed writing this perspective with Shriram, Christina, and Mark. And in particular, I learned a lot, for instance, the distinction between violation of a law and a deviation from the law. Okay, so as I mentioned, we are interested in self-organization principles in living systems. And the core of the work that we do is basically try to uncover the complex and varied interactions that arises between these living entities, and what are the emergent and resulting collective behavior, and what are the functional roles of these states. Now, one of the things that I kind of find very exciting is the fact that biology, of course, gives us tools to be able to extract really beautiful information from the system, and this is kind of gives us an arena to do quantitative work and kind of be able to really understand this phenomena from a quantitative perspective, and that's what I will be sharing today. And of course, as an experimentalist, our hope is that the fundamental self-organization principles that we discover goes beyond a particular system, and so there is a notion of universality there. Yet we need model systems with rich phenomenology of self-organization principles. And I always say that we need hydrogen atoms because hydrogen atom was this quintessential test case for understanding the behavior of atom all the way to Bose-Einstein condensate, for instance. So I'm going to introduce you to the periodic table of the talk that I will give today. And this is the phylogenetic tree, which traces the deep evolutionary roots of the species we study, the repertoire of the species we have in the lab. And I've highlighted two major transitions here, two major evolutionary transitions. One is the emergence of multicellularity, and the other one, emergence of bilateral or bilateral symmetry. And these transitions kind of like we look at marine organisms, and I think it has helped us really kind of basically inspire the scientific questions that we try to address in the context of collective behavior. And very recently with the sponges or multicellularity, this question of function, emergence of function and behavior within these systems. Now, much of the talk will be focused on bilateria, and this is obviously a major clade that includes a vast majority of the animals, and we study echinoderms, and I'm going to focus on sea star in particular. They're exceptional because they start from a bilaterally symmetric larvae, which is what we will be calling particle in this talk, and then they develop into pentameral adult symmetry, which on its own is a very interesting question. And then, as I mentioned recently, we are interested in understanding the function and behavior of these states, and that's where we kind of start looking into evolution of multicellularity by looking at porifera or sponge, which is basically at the base of this type of evolutionary transition. And the main question that we try to address kind of like in our lab is basically try to understand what are the interactions between these individual organisms. So I will say we try to understand what this interaction matrix is. Are there internal inherent states for these particles? And you can see they can have a range of different interactions at the level of 2 particles. And then eventually, based on these interactions, what kind of collective states emerges? What are the macroscopic phenomena that we get in this type of systems? And I'm going to kind of like walk you through how this type of interactions can give rise to a range of very intriguing properties at the macroscopic level. And again, the punchline is that we have a number of different broken symmetries in this system. Time reversal, of course, these are non-equilibrium systems. We have systems that can break a chiral symmetry, reciprocal interactions, and then we're going to see what kind of features emerge. Now, let's focus on the particles that we will be looking at in this talk. So this is an embryo of a sea star. It's at the gastrula stage. And if this is a zoomed-in view of this embryo, and you can see that it's slightly elongated along an axis of symmetry, which we call anterior-posterior axis. You also see that it's entirely covered in these elongated structures, hairy structures that are called cilia. The cilia is an active polymer. It's been shown in previous talks as well. They can beat synchronously, and this beating pattern that they generate involved in actually induction of left-right asymmetry in many organisms, including us. So this is a still image. Let's look at the dynamics. You can see that, again, it creates this metachronal waves that can push the fluid around and basically will be responsible for how they can swim around in the environment. Now, let's look at what happens when we release them in the environment. How do they swim? So first, we're kind of going to look at the side view of these. And you can see this is the AP axis. And we have a water-air interface. The particles you see in the bottom are the actual embryos. And then you can see the reflection of them at the water-air interface. And you can see 2 types of behavior emerges. First of all, they have this kind of corkscrew-type motion. They come to the water-air interface. And if you notice, first let's focus on this one. When they come to the water-air interface, that corkscrew motion transfers to basically a spin dynamic. So you have stable spin at the water-air interface. So this is what I'm going to call a spin. But there is another behavior that can emerge, which is some of them, they can come to the water-air interface. This is this example. And they can attain a finite angle with respect to this water-air interface, and then they precess about their axis of rotation. And this is what I'm going to call the precision, or I would also sometimes call it orbit, though it's not precise. But what I'm going to show you is that these 2 internal states can actually result in 2 different macroscopic behavior at the large scale. First, I will focus on what happens if you have a collection of spins together, and then I will focus on what happens if the system can switch between a spin and this precision. Now, of course, we have an object that it's a tippy top. So what do you do with it? And we decided to put a large number of them together. And we observed this really beautiful phenomena that's still, it's been a few years, but still I'm really amazed every time I look at it. So now instead of looking from the side, we're looking from the top. So this is kind of like a petri dish. And what you will see is that you kind of like these particles are spins that are stable at the water-air interface. And note that this is a large field of view, and this is a time stamp to give you a notion of scale and time. And what basically we observed was this, what I call a constellation of sea stars. You can see that they come together to form what we call a living chiral crystal structure. This structure persists for very long times, This is in the order of days. And it basically, the whole self-assembly dynamics and finally the solution of this crystal, so this is a looped video, is entirely controlled by the embryo's internal developmental program. So the particle is basically has an internal time, and this is kind of going through this, and that's why you start forming a crystal and then eventually dissolve. And again, this is a phenomena that you can observe with eye. I also love to show this because this is a 6-well plate. If it means anything to you, it's just a few centimeters across. This is the initial formation of, you have a few centimeters of water here. This is the initial formation of this kind of like crystal. So you have nucleation. And then these kind of like the regions, they, as you saw, they rotate and then kind of start merging together and forming a crystal. Now, I'm going to first briefly talk about what happens if you have, if they only have their spin degrees of freedom. So there are only spins that come together. And as I mentioned, we are interested in understanding or uncovering what are the interaction forces between them. So kind of if you look at the two-body problem, you see that you obviously have hydrodynamic interactions, and that hydrodynamic interaction results into an attraction force. Of course, you have steric repulsions. The nature of these forces that are longitudinal are reciprocal. I'm saying for now because now we have a way to actually also make this non-reciprocal. This would be the second part of my talk. And then once they come together, because you have this kind of like hydrodynamic interactions at the interface, and I won't go into details, but from lubrication, you also have ciliary interactions at the interface. What you can see is that we have an additional exchange of transverse force and torque at the interface, and this basically, these are non-reciprocal microscopic interactions, and you can clearly see that they have this dance kind of around them. I would also mention that this is kind of like actually a very generic feature of this swimmers, a class of these swimmers, and first observed by Knut Drescher and Ray Goldstein. They called it, for the case of volvox, and they called it a dancing volvox. So the first thing to note is, of course, because of the pre-stress that arises from this transverse force exchange and torque exchange within your system, you get a Goldstone mode. So your system breaks chiral symmetry, and it basically rotates. Now, I won't go into, I want to kind of like be able to get to the later part of my talk, so I won't go into details of looking at the ground state of this system. I'm going to focus on the excitations within this system. And in particular, this kind of like observing the excitations was really our foray into kind of trying to understand how these non-reciprocal microscopic interactions can give rise to macroscopic non-reciprocal response in this system. So to do so, we're going to subtract that global rotation and then see what happens. And what we saw was that under certain kind of excitations, what you end up seeing is global, basically self-sustained chiral waves that go through the entire system. Eventually, they damp, yet they're quite long-lived. And of course, this is an overdamped system. So the presence of such kind of stable and eventually damping oscillations was, of course, quite a surprise kind of coming from classical mechanics. And to better visualize this, we can basically look at kind of like the displacement field. This is looking at the displacement angle, and you can clearly see the existence of this chiral wave, chiral displacement wave that goes through the entire body of this crystal. Again, very large, long-lived, and embedded in a fluid medium. Now, at around kind of like same time, in fact, in that KITP meeting, I heard a talk from Vincenzo and their group that this really beautiful work where they show that by waiving the standard requirements from linear elasticity, in particular energy conservation, one can unravel unexpected mechanical behavior that previously been overlooked. And this is because entirely new moduli appear in the stiffness tensor. And these are kind of off-diagonal components. They're termed this odd elasticity. And what they show that now, basically, the system can actually couple different modes of stress and strain within the system. So you can have a material where you push it, it actually can rotate. And again, this is kind of like because of the fact that you are removing this energy conservation constraint in your system. Now, there are certain predictions for what odd elastic material would do. And if we go back to our interaction matrix, we can in fact coarse grain from those interactions. And what we see is that coarse graining those microscopic non-reciprocal interactions indeed gives rise to a Maxwell-Betty non-reciprocity, or the emergence of this type of odd elastic moduli in our system. So we came up with ways of quantifying that looking at the strain fields around defects. I won't go into details of it, but one of the kind of like emergent features of this odd elastic material is that they can sustain this type of oscillation in their strain space. So if we look at our crystal and basically go over the boundary and look at the four principal components of the displacement gradient, and then you can see basically that you get this kind of like oscillations that emerge. So this is from the experiment. But also note that these oscillations eventually decay, and of course that's because you also have even like material itself is going to be kind of responsible for this decaying to happen. Okay, so this was looking at the fact that your particles have are spins. But as I mentioned later on, we kind of like got to see that this system, in fact, has a range of interest strength features. So I call this living chiral crystal 2.0. And what we noticed was the fact that you can also have the precision of axis of rotation. So this other mode, internal mode. And I showed you these two side views of how they kind of like, you can get this type of precision. And in fact, we think that this precision, if you look at the bulk movement of your collection of embryos within your system, you can see this kind of like trajectory. So these are maximum intensity projections. You can see that you actually can have different helix kind of like angle. And the reason that we think that arises is because these particles have an internal force and torque vector, and that can be aligned or misaligned, and that can give rise basically to this additional internal state. Now, kind of like the story wasn't so linear. The reason that we realized that the particles have this additional internal state was the fact that in many of the experiments, it was actually very easy to get kind of like spontaneous oscillations in the velocity field. And this is an example of that. So this is a very large crystal, as you can see. And what we're going to look at is the velocity in the x, y, and direction. We're looking at the center here. This is easier to see. And you can see that basically the system starts kind of like getting excited into this oscillatory state from the fluctuating state. You can clearly see kind of like this signatures of fixed amplitude over long periods of time oscillations. And then eventually it kind of like dies out, but it looks like more of a transition into the fluctuating state. Now, of course, when we realized that you can have these two internal states, one of the questions that we wanted to understand was, is there a possibility for us to do a data-driven approach to be able to get a dispersion relation for this system to kind of really understand the contributions from these two types of inherent internal states? And this is a collaboration with my colleague, Jorn Dunkel. So what we did was basically a combination of a temporal data-driven approach to get the modes. So this is using dynamic mode decomposition, and as well as a graph Laplacian eigenmodes to get the spatial frequencies. And basically what we saw is that, I'm going to play the video. So this is the dynamics of our crystal. And then you can actually see that a low-rank representation using only 9 modes is indeed can capture the main bulk of the dynamics that we observe. And we see that there are actually 3 groups of modes that describe this system. A global rotation, which of course is the Goldstone mode. And then we have these kind of 7 modes in this 9-mode reconstruction. 7 of these modes correspond to a long wavelength, low frequency modulations. So this is reminiscent of having acoustic vibrations in an elastic solid. And then we have 2 additional modes that correspond to highly localized, high-frequency circular motion about the embryocentroid, and this is consistent with precision dynamics. So what it tells us is basically these modes come from the fact that you have spins, and these modes come from the fact that you basically just have this precision. Now, before I only focus on these 9 modes, I want to show you the dispersion relation in its full glory. And I'm really excited about this because it's very rich. There is a range of interesting features to see. The first thing you observe is basically kind of like you have these kind of bands, which are optical bands, in fact. And this happens in a 2D triangular lattice without sublattice symmetry. So it really comes from this kind of like active degrees of freedom. You have nonlinear branches, you have interactions between acoustic and vibrational modes, and you also have a resonance. You have this kind of like negative, there is a lot, and I think for us it's basically has opened up this a whole range of kind of opportunities to try to understand in this system, but also like a lot of people here are interested in designing materials, and you kind of like, you can start thinking about how you can play with internal states and other features to be able to design dispersion relation like this. Now, very briefly, I'm going to go back to, the 9-mode that was kind of like enough, at least, to get the major features of our system. And again, you have these optical modes, which were kind of surprising because they have a finite frequency even in the kind of like as the Q goes to 0. And then the acoustic modes, this is in the oscillating case. The acoustic modes actually have this quadratic behavior. This is a feature of their odd elasticity. And then you see that as the system transitions from oscillating to fluctuating mode, these optical modes basically disappear. Okay, I would just mention one last thing, kind of like going back to the fact that we can get both the imaginary part and the real part of our kind of frequencies, and the kind of like spirit of non-Hermitian systems. Actually, what we showed was that you can look at the kind of like the slope of this kind of the fit to this data, and indeed this slope gives you the ratio between odd and even moduli in your system, which was also consistent with how we could get it from strain displacement fields in the crystal itself. Now, what's kind of quite amusing is now you have a system which can have an odd elastic kind of feature, but it can also have this, what we call a form of active gyroelasticity in some sense. Now, the mode decomposition has a lot of, I think, has opened up a lot of possibilities, and this is kind of goes back into kind of these questions of how do we quantify energy cascade within the system, how do we quantify information cascade within the system. So this is something that I'm very interested in. So we've been looking at mode-mode correlations. Obviously, if it was an equilibrium system, you wouldn't get this off-diagonal mode couplings. So these mode couplings can tell you something about nonlinearities, non-equilibriumness. You can look at antisymmetric correlation functions in time. And you can also look at mutual information between the modes, and this basically gives you an opportunity to start looking at information transmission within the system. Again, for us at the moment is a way to be able to come up with concrete ways of quantifying these features. And last thing I will mention here is that if you construct the dynamics using only the vibrational modes, or acoustic modes, and then basically construct a phase space in the strain space and velocity space, you see that you get this type of cycles within the phase space, and these cycles is basically the emergence of a system that can do work on different types of work indeed on the environment. And now one can think about like efficiency and everything. I'm gonna just quickly kind of like, so there's a way to, we can write down kind of coarse-grained equations to describe this, but I'm going to skip that because the question we next wanted to understand was these are spontaneous oscillations. We wanted to see whether there are controlled ways of being able to excite this. And the first kind of like, I'm going to walk you through a series of what we call protocols that we are going to do on the system to be able to do this. The first set of these protocols are going to be basically a mechanical perturbation in the kind of form of having a C-shaped chamber, confining your crystal, and then applying a step compression. And indeed, you see that kind of after applying a step compression, you can excite this type of oscillations within the system. It's not kind of, it turns out to be a Goldilocks situation, so you actually need to be at a kind of like a sweet spot for compression strain rate, which we also understand from our theoretical model. But once you are in this compression strain rate, you can see that you can basically excite this sustained oscillations here. But what other things you can do is I call a successive compression protocol, because what it does is that by successively compressing, you're removing the tilt degrees of freedom from your system. So what you end up with is basically initially oscillations that can come from both tilt and spin, but eventually your system is only oscillating just because there's no kind of like tilt degrees of freedom left. So you can start thinking about kind of like this the work that can be generated from an odd material versus this other degrees of freedom. My favorite experiment, which was a very hard experiment, but of course it was done by an amazing graduate student in my group, is oscillatory compression protocols. And you can imagine you can change a lot of features here. And here what you basically see is that this type of protocol mainly gives you odd elasticity within the system. You can see that the system kind of gives you this interesting path when you do this type of apply this type of protocol. And again, there is a lot that you can explore here. And of course, eventually our hope is that to be able to extract this work from the system. This was just a way of showing that kind of like how you can build a wheel of time reversal asymmetry. How many minutes do I have? 2? Okay. All right. Maybe let me just quickly say one last thing about this. Okay. So in the first part of the talk, non-reciprocity was coming from transverse interactions, and longitudinal we had reciprocal interactions. What we end up thinking about was, is there a way to actually also introduce additional non-reciprocity by kind of like mixing particles of different developmental time? So initially we had all blue particles, but now what we do is we start experiments where we kind of let some of the particles develop to later developmental stage, and then you have this delta T in the development time. And of course, you can see that particles have different shapes. They have different fluid flows. So what happens is that when they come together, they actually also in the longitudinal direction, they have kind of like non-reciprocity. So you can see that they actually behave like a run and chase type dynamics particles. And what this means is that now if you put a large number of them together, now you don't just get the fluctuating state, which is the crystal state. You can get traveling, you can get emergence of a polar order within the system. And unfortunately, I'm running out of time, but there is kind of like we've been using inference kind of like techniques to extract this kind of longitudinal non-reciprocal interaction, tune it to be able to map the phase space of the dynamics you can get, and then kind of like I guess the next step for us, which I will just leave it here because there were discussions about landscapes, is kind of like it turns out that for these systems, polar order will not just be enough to describe the system as you change non-reciprocity. As a matter of fact, the structure matters. And the way we handle that is basically looking at kind of like a local structure within this system by introducing topological features, like looking at the topological motifs within the system, like how many, for instance, T1 transitions gets to go from one of these motifs to a perfect crystal. And this can kind of like eventually gives us a landscape where, for instance, M1 is a perfect crystal, M2 is a defect, and you also get this asymmetry in the direction of M1 and M2, and then you can see what kind of transitions you get as you change non-reciprocity within the system. So this is kind of like simulations. You can see it looks like a first-order phase transition, but you can also do it in the experiment and then kind of like see how your system actually flows one state to the other state. We call this a flowscape. And kind of going back to what Sabina was talking as well, I think there's a lot that you can also learn from kind of like looking at what we call information length, which is actually kind of very close to this idea of geodesics and kind of measuring that length. And you can see the system actually has different rates in the fluctuating and traveling state. And I know I'm out of time, so I'm just going to leave this here to kind of like say that this system, there's a lot of ways to be able to control this. And I think it really gives us an opportunity to think about and quantitatively analyze this type of systems. But also, of course, the next step for us is to understand what's the function of this state. Obviously, it's a large phase space. What's the function that emerges from each of these collective states? And with that, I will be happy to take questions.